Let's proceed to the next talk. As I said, Olga Loginova is the representative of the winning team at the hackathon in Edinburgh. They worked on the Amazon-provided challenge, industry-inspired challenge, we called it, on hallucinations in large language models. So, Olga, we're very happy to host you here. The floor is yours. Please continue with your presentation. Thank you.
And thank you very much for the introduction. Thank you very much for the opportunity to participate in the hackathon and to present here. I'm going to talk about hallucinations in large vision language models and specifically how we can reveal them through self-consistency. First of all, let's define hallucinations. Hallucinations in vision language models is some sort of misalignment, disagreement between the image, its content, and what text was generated by the model with respect to this image. Through hallucinations, we can test models for its robustness and reasoning capabilities. We are specifically interested in the direction from image to text, and the majority of benchmarks for this kind of hallucinations, given text and description, try to assess the text that generates the model, maybe manually, maybe through some other LLMs, or they try to classify, given the image and the question about this image, basically mostly it's yes or no question, they try to classify and assess the performance of the model through accuracy. In our task, we wanted to combine both of them and assess both tasks within one model and see how consistent the model is with respect to the provided answers. So, first of all, we hypothesize that models are consistent between generation and classification. It means that they are non-contradictory. Also, we think that not enough information and too much information are both detrimental for the models, and they start hallucinate because of that. And third, we think that less close images create a higher rate of the hallucinations because our task was based on comparing pairs of images. For this, we opted for a Dochi dataset by three main reasons. First of all, this is a relatively new dataset. It appeared in the end of April, so we expect that none of the models were trained on the dataset. And it's not in the training data. It has quite detailed descriptions to any image in it. On average, 136 words, and hallucinations may appear in objects, properties of object, or relations between these objects. And this description covers them all in great detail, so it's kind of easier to pinpoint the hallucination. Also, the dataset was specifically assembled to cover substantially similar and contextually related groups of images. And this is very essential for our task because we feed a couple of images to the model and see its reaction. So what we did, we took 80 image pairs from this dataset. We collected them by clip cosine similarity from 0.65 to 0.95. Then we gave two prompts for these pairs of images to the model. First is a generation prompt when we ask the model to compare these images and find the similarities between them. And then we feed the same pair of images and the statement that the model generated back to it and ask if this statement is applicable to one of the images or to both of them. Here, what we did in detail. First, we decompose, in a sense, the model. We first fed the model only with images, asking for finding similarities and only with text, only with the detailed description and asking for similarities, and with both of them. And then the model generated some statements. Some of them could be true, could be false, but we are more interested in consistency, so we filtered out complete nonsense and we left even the wrong statements because we wanted to see the reaction on the second round with evaluation when we give the same images to the model and this statement it generated to see if its reaction back. So with the applicability of the statement to both pictures or one of them, the model could react either way. Either it could say that this statement is applicable only to one of the images, like in this case, where both cats are white and black features, which is the correct statement in the beginning. The model could hallucinate and define it only to one of the images. And on the other hand, it could be vice versa. When the first statement is incorrect, both tops have a drain cover, and we see clearly that only one of them has this drain cover, and the model answers the correct answer, gives the correct answer, which is one of them. But for us, it's also a sign of inconsistency in it. Once again, we take the images, descriptions through different modalities and generation problem. We feed it to a vision language model. With respect to each modality, it generates statements. All in all, we have 1,200 statements. We take them back, feed to the model with the pictures and descriptions, once again, are separated by modalities, and give the evaluation prompt, and it could output a classification answer, either one or both images. So what we did with the models next, the experiments themselves. Here, I would like to recall the overall architecture of models. The vision language model, it has visual encoder, it has language decoder. Visual encoder could be CLIP, CGLIP, GLIP. Language decoder could be Llama, Mistral, Phi. And the majority of them now have adapter on them to make them more efficient. So this is the picture from Bunny paper, but it represents more or less every vision language model. We took four models. One of them is Bunny, as I already mentioned. Another one is Mini CPM, which is kind of close in settings with Bunny, same visual encoder and with different amount of parameters, same LLM. We also took Lava, which uses different visual encoder and different LLM CLIP Mistral. And we also took Claude, thanks to Amazon, Haiku. And for us, it's a black box. We do not know what stands behind in Haiku. So what we see in the results, first of all, we see that there is no consistency, no generalizability for this model. So within each model, the trends are different. We clearly see that in Lava, we have quite strong language modality. Visual modality is not that strong, and both modalities are also so-so. We also see that for some models, images are stronger, image modality. For some, is weaker. In some cases, both modalities perform better, or in some cases they perform worse or equal to the text modality. So it's very individual in a sense. Also, we're diving deeper into the results in the confusion matrix. We see that consistency more or less okay in Haiku, first of all. And its image modality is very weak in Lava. Also, the opposite modalities from generated by image and then assessed with text, generated by image and assessed with text, for all the models is quite weak, weaker than text modality, and same more or less for Bunny, and the opposite direction from text to image. Quite individual, quite interesting. Overall, we also wanted to see how low similarity of the images and high similarity images are opposed to each other, but we didn't see many trends to say. We would say there is no much difference in it. Except for the thing that in low clip similarity, we see on very weak this trend from image to text part. Coming back to our hypothesis, the first thing we wanted to know that models are consistent. We wanted to make sure that they are consistent between generation and classification, and we found that they are not. And we saw this in the pictures scattered. Hallucinations can be caused by both not enough information and too much information. This is confirmed to some extent during the qualitative analysis, and we can see when, for instance, when the blurry background could be a source in the image, could be a source for hallucinations, like the model implies something that on the second image, also in the first image in that blurry background. Also prompting for similarity with dissimilar images will lead to higher rates of hallucinations. This is also not true. We saw that in the previous pairs of confusion matrices. So what coming to the conclusion, we see that modalities have very different effects with respect to each model. And also we would like to understand why this performance that we have in self-consistency with the models is so different to what we can see on the hallucination bench, the main benchmark for detecting hallucinations, which works exactly the way I explained at the beginning with yes/no questions on it. So here is the leaderboard from Hugging Face when we see that, well, Lava is the worst, okay, for hallucination bench, but at the same time, Mini CPM as if performs better than Haiku, but we do not confirm it with our self-consistency experiment. Then we saw that actually the lower similarity or high similarity do not lead to more or fewer hallucinations, but we expect that the nature of these hallucinations is a little bit different, and this is the way we would like, this is the direction we would like to explore more in this. So basically this is it. Excellent. Thank you very much.
Olga, thank you so much. Let us speak, Olga. It was fantastic work. Well done, Olga. And, you know, the Amazon representatives there at the room, at the hackathon room, were very impressed by your work. Well done again. And I hope you enjoy some of the little awards. We have time for one very quick question, if there is any, because I understand that people now are looking forward to the lunch break. Any questions? No? Okay, let's thank Olga again and the morning speakers. We are very grateful to them. Thank you so much.
Thank you.